Thank you.
Anyone else? Okay, the combined cycle is, if you remember in chapter 9, we had a combustion chamber, we had a compressor, and we had a gas turbine. Then at this part, we had a heat exchanger going back to the compressor. This was our cycle. Now in chapter 10, we have a boiler. That's our pump. That's the condenser. And that's our steam turbine. So this is basically the two cycle look like. Now, if I take this cycle, run that, and capture the heat here, replace the boiler. So that capturing heat becomes a boiler for my steam cycle. Then I have the two cycle together. I have two turbines, one pump and one compressor, and one combustion chamber only. One Q in, one Q out. Yet I have two large, turbines that I get the benefit. If you remember when we were talking about chapter 9, Brayton cycle, we said this is the most inefficient cycle to generate power. However, if you combine it to steam cycle, then both this cycle independently inefficient. This is simple Rankine cycle, this is Brayton cycle. You combine it together, they become very, very efficient. Now, almost every utility companies in the nation and some around the world have this combined cycle. There is a Harbor Generating Station in San Pedro that belongs to Los Angeles Department of Water and Power. They have 4 units of combined cycle. Generally, they use that during a peak power time, but sometimes they have one of their power plant shut down or one of their units are shut down, so they can run those. So they're always available to them. So that's, again, this is what we're going to do. So let me see. Where is all that? So this is our point one. We come out at point two. We're going to quote unquote the boiler coming out at point three. This is our point four. And that is our simple Rankine cycle. And then I get the work out here. And this is my Q out. At the top cycle, air enters at point five, the compressor coming out at point six, then coming out of the combustion chamber at point seven, then out of the turbine at point eight, and finally here, point nine, when it goes to exhaust. So I have one Q out here and one Q out between points five and nine for the top cycle. So this is our gas turbine cycle, or let's call it the top cycle. And this is our bottom cycle. Now, before I erase that, once again, November 17, which is second test, and it's chapter 10 only. So at the end of the class, I tell you what's going to be on your test. Now, since this is two separate cycles, this cycle working fluid is air, this cycle working fluid is water. As you can see, they never get mixed with each other. The hot gas coming out of the turbine go inside the tube of the heat exchanger. The water coming go over the tube, gain the heat from the surface of those tubes, and then become steam and run the steam turbine. That's the whole concept. The net energy within this heat exchanger is zero. Whatever comes out there will gain by the bottom cycle. So let me first do the TS diagram. The TS diagram is very, very simple. First, look at our steam cycle. We know the steam cycle as a dome. So this would be my point one. Isentropically go to point two, point three, and point four. Very simple. Now the top cycle is air, has nothing to do with the dome because air does not change phases. The reason we have a dome to show the change of the phases of the water. Now I can start from here, 0.5, going up isentropically, 0.6, that's the work of a compressor. This is 0.7. 8, and this is 9. It doesn't matter where that line comes right in here, 0.9, even if 0.9 is here, it's no big deal because 0.9 has nothing to do with the bottom cycle. Again, this is our top cycle. This is our bottom cycle. So the TS diagram, you draw the TS diagram completely separate from each other. They don't get mixed, no complications, very easy to do. Any questions? Now,
Excuse me, Professor.
yes,
So for TS diagram, you would want us to do like two separate, or just like on the one that you have like them on top together in one?
that's what I did. It's just, I do this separately and I did this separately. You can start 0.5 anywhere. This is arbitrary. It's
Okay.
into scale or anything. So you do this one first, that one second. Where these points located, nobody cares.
Okay.
All you do, you're showing that this is different cycle than this is than the bottom one, because this one has phase changes, saturated line. This one has nothing like a saturated line involved because it's air. Now, our focus should be what is happening in this heat exchanger. In this heat exchanger, the Q out of this heat exchanger, what comes out between 8 and 9, is going to gain between 0.2 and 3. So what we can do, we can write basically the relationship between it. So let me, I'm going to write it somewhere that I can. Okay. At the top part, we have mass of air times H8 minus H9. This has to be equal to mass of water, this cycle, between H3 and H2. This becomes very important because knowing one of the masses, like if we know the mass of the air, then we know how much water we have to push through this in order for this cycle to work properly and provide the power that we need. So that relationship that we just established is going to be very crucial in order to basically solve a problem. Any questions?
Professor?
Yes.
Sorry, I can't really see the H values at the top. Does that say H8 minus HG? Or is it?
That's the second.
Thank you.
The mass of air times H8 minus H9 has to be equal to mass of water times H3 minus H2. H3 minus H2, that's, before we had boiler. Now we have this exchanger acting as a boiler for this cycle, acting as a Q out for this cycle. So H8 minus H9 has to be equal to H3 minus H2 multiplied by the respective masses.
Thank you.
Right? All right. Any other questions? Now let's see if we can do an example so we can understand this better. We're going to start with the top cycle. The first assumption we make in the top cycle to make it easy for ourselves, that Cp and Cv are constant. So we can use all ideal gas equations. Now at the top cycle, I have at 0.5, I have T5. Is it okay if I erase the equipment arrangement?
Yes.
As if I can do that, then it's easier to, I have to eventually erase it, but I'd rather erase it now.
Yeah,
before-
you could erase it. That's good.
All right. Okay. Because all the information we need to have, I'm gonna transfer it to there. Now, for the top cycle, we have T5 equal to 300 degrees Kelvin. We have R of P equal to 16. And what else I have there? T7 is 1500 degree Kelvin. And T9 is 420 degrees Kelvin. These are the information at the top cycle. At the bottom cycle, I have condenser pressure will be 15 kilopascal. I have the boiler pressure to be 10 megapascal. And temperature at 0.3 is 400 degrees Celsius. That's information for the bottom cycle and is for the top cycle. The big assumption is that we have CP and CD are constant. So the best way to solve a problem like this, you solve each part, each cycle completely separate. You find, the Q in, you find the Q out, you find the network from the top cycle. You do the same thing, you find the network from the bottom side. Since you have only one Q in and you add the network together, you find the overall thermal efficiency of the cycle. So once again, this is work of the pump, work of the compressor, Q in, work of a gas turbine, work of a steam turbine, Q out, so we transfer everything in our diagram to our TS diagram so we don't get confused as we go through this. So since I made that big assumptions that CP and CD are constant, I can easily say T6 over T5 is equal to P6 over P5 to the power of K minus 1 over K. P6 over P5 is given, this is my R of P. So I have here 16, K is 1.4, T5 is 300, so I can very quickly find the value of T6. Six, 2.5 degree Kelvin. Now, similarly, I can find T8. So T8 over T7 would be T8 over T7 to the power of K minus 1 over K. T7 is given to be 1500. And this is going to be 1 over R of P, which is 116. So from there, I can find the value of T8. To be 679.3 degrees Kelvin. So I have all 4 temperatures in that cycle. So I can very quickly find the Q in from that cycle. So the Q in, by the way, the mass of air was given. To be 14 kilogram per second. Now we know that Q in is equal to mass of air times H7 minus H6, which is equal to mass of air times Cp times T7 minus T6. I'm replacing that with a heat transfer equation. So now I can easily find the value of Q in. I have all these numbers, and this is 1.005. Mass is 14. T7 is 1500, and T6 662.5. So my Q in value would be 11,784 kilowatt. This Q in is the only Q in for the boat cycle because I had only one combustion chamber. There's no Q of the boiler here.
Professor, quick question.
Sure.
The for the P6 over P4 and the P8 over P7, where were you getting the P6 and P8? I see the RP, but don't know where you're getting the P values.
P6 over P5
Mm-hmm.
is our pressure ratio.
Mm-hmm.
Before we call it 1 and 2. Now the number is changed, 5 and 6. So larger pressure over a smaller pressure give me a pressure ratio.
Mm-hmm.
The opposite of that, 8 over 7, would be the reverse of this. This is chapter 9, Brayton cycle. You forgot already?
I was just thinking, do we have any of the P values for those points, or we're just using the pressure ratio for those?
What do we need another pressure? This is an air cycle. We don't need anything. On the air cycle, we need 2 temperature and a pressure ratio. That's it.
Got it. Okay.
And I want you to do me a favor. Go back in chapter 9. Take a look at the Brayton cycle, definition of a Brayton cycle. Then we have a pressure ratio and we have the temperature. And this time we assume that this is constant. If it wasn't, we have to go to air table, find, H values at 0.5, at 0.6, and 7, and 8, and 9, and then go throughout the table, find this Q in. So we don't need any pressure. All we need is 2 temperatures and pressure ratio. If it was cycle, we needed just a volume ratio, which is we call it compression ratio. So you need to go back. So you can't afford to forget this because you're gonna come back and haunt you on the final exam. Please understand, I'm not trying to pick on you. I'm just trying to refresh your memory. You need to go back and look at it.
Got it. Definitely something I need to review. Thank you.
Yeah, no problem. We don't need to have any pressure anywhere else. So that's the top part. I still need to find a network. One of the ways that I can do that is I can say, work on the compressor, again, is equal to mass of air times H6 minus H5, or mass of air times CP times T6 minus T5. With that, I can plug in the number and find the work of a compressor. Becomes 5,100 kilowatts. Now I can find work of a turbine, gas turbine, which is mass of air times H7 minus H8, which is same thing as the mass of air times CP times T7 minus T8. And this will give me the work of a turbine will be 11,547 kilowatts. So the network of a gas turbine cycle or breakthrough cycle would be the difference between these two. So the network of that becomes 6,447 kilowatts. This is a network from the top cycle. I need this queuing, I need this network later. I'm done with the top cycle. So now I can go take a look at what is happening in my bottom cycle. This is simple ranking cycle. At a state 1, I have P1 equal to 15 kilopascal and X1 being equal to 0. So I find the value of H1 and V1. H1 value would be 225.54 kilojoule per kilogram. And value of V1 would be 0.001014 meter cubic per kilogram. At state 2, I have work of a pump, which is equal to H2 minus H1, and that is also equal to V1 times P2 minus P. From there, I can find the value of H2 to be 236.46 kilojoule per kilogram. That's my second pump. I'm sorry, my second H value. I need to find 2 more H. So now, at state 3, I have P3 equal to 4, equal to 10 megapascal. And I have temperature T3, which is 400 degrees Celsius. So I go to superheated table, and I find H3 and S3. The value of H3 is 3,097 kilojoule per kilogram. This value of S3 is 6.214 kilojoule per kilogram degree. Count, that's the third H value. Finally, at the state 4, I have P4 equal to 15 kilopascal and S4 being equal to S3. From there, I gotta find S of F, S of F of G, H of F, H of F of G, H of F, I know what that is, which is 225.54. Now, the H of F of G is 2372.2. My S of F is 0.75. 49, and S of F of G is 7.252. From this side, I will find the X value. And once I find it, I use these values to find value of H4. So if I do that, my X4, which is S4 minus S of F divided by S of F of G. This will give me the value of X4 0.7548, and therefore H4 value, which is H of F plus X4 times H of F of G. Once I plug the number in, I get an H4 value of 2011.48 kilojoule per kilogram. So now I have all the H values for this cycle. So now I can basically find work of a pump is the, I don't have the mass of water. So at this point, what I'm going to do, since I don't have a mass of water for here, I'm going to use this relationship that I developed at the beginning in order to find the mass of water. So I have mass of air. I'm going to replace it with the heat transfer equation times Cp times T8 minus T9. That has to be equal to mass of water times H3 minus H2. And if I look at this, I have T8, T9 was given to me. I calculated the value of T8. Mass of air was given. Cp is 1.005. Mass of water is unknown. I found H3 and I found H2. Through this relationship, I can find what would be the mass of water. In this case, the mass of water becomes 1.275 kilogram per second. This shows me, in order for this system to work under the condition that we have, for every 14 kilogram of air goes through the top cycle, I need only 1.2 kilogram of water going through the bottom cycle in order to balance it out. That's why we write this relationship between this part and this boiler and the Q out of the other cycle. Now that I have that, so I can write work of a pump is equal to mass of water times H2 minus H1. I have all these values and I just calculated mass of water. This will give me the work over pump value of 12.91 kilowatt. Work over turbine, which is a steam turbine, is equal to mass of water times H3 minus H4. That will give me 1384 kilowatt. The difference between these two will give me the net work for the top cycle. So the net work, for the lower cycle, for the steam cycle, would be the difference between these two. And that becomes 1371 kilowatt. So now I have the network on the top cycle and the network on the bottom cycle. So I don't need this equation anymore. I'm going to erase the TS diagram. Now to find the overall thermal efficiency, the network total would be the network of gas turbine plus the network of steam turbine. So if you add this number and this number together, you find the final network I can call it O and O. Maybe this is better. The value becomes 7,819 kilowatt. Now, what's the thermal efficiency? Again, overall is equal to the final network divided by just 1 QE. So that would be overall network divided by QE. I have both values. If I do that, I get a surprising 66.5% efficiency. If you remember, simple Rankine cycle had only 26% efficiency. Then when we look at ideal gas, gas turbine cycle, that also has about 27, 28% efficiency. By combining it together, we make two inefficient cycles. It's the most efficient way of generating power. And you see how much efficiency we get that we never seen this before, 66%. Of course, if we had efficiency of the compressors and turbines involved, these numbers would probably drop to about 50%. And still, it's very good, very high. Because neither one of those two cycles by themselves capable of producing that kind of a thermal efficiency. Any question? I know this is a mess. Please feel free to let me know. I can walk you through it one more time. I have no problem. You sure you don't have any questions? Okay, well, keep in mind, if I wasn't making this assumption, CP and CV are constant, this problem would have been much more time consuming than what we did here. Because in just a matter of few minutes, we found everything for the top cycle because we didn't have to go to the table. Very quickly, we find out the two temperature, and we found the Q in, work over compressor, work over turbine, and the network from the top cycle based on the temperature value. If it wasn't, as you recall, we had to go to the table at a state one, find H1 and PR1, then for a state two, saying PR2 over PR1 is equal to, P2 over P1, then find PR2, then go to the table, find H2. As you can see, it would just keep on dragging on, and you get into a point at point H2, H4, we needed to have a lot of interpolation. And that would be very time consuming. But assuming that this is constant, made our lives much simpler. If this was not constant, this will give us about 64%. With all the headaches that we had to go through, still would give us a very high percentage. So that's why this is very, very popular in all utility companies. So the last project I did, it was in 1991 or 1992 at Department of Water and Power. That was my last project that we purchased 4 GE turbine, each one 120 megawatt. And then we combine it with our ranking cycle or steam cycle, and each unit gave us 400 megawatts of power. So total of 1,600 megawatts of power in one power plant. And that's located in San Pedro. And 2 years ago, before the pandemic, I took my student there. They took a tour and they realized how they saw the gas turbine, they saw the steam turbine, they saw the heat exchanger. It was amazing, just seeing the look in their eyes, taking picture of all this equipment. Some of them they had video camera and just taking videos. And it was pretty interesting tour. Unfortunately, we cannot do it now. Hopefully one day things goes back to normal and we can start doing that. Anyway, this is the last part of the chapter 10. Now, let's see what's going to be on your test in chapter 10. You know, we don't deal with the Carnot cycle, so we don't need to worry about it. We're not going to deal with a simple ideal ranking cycle, because that's just the beginning of the introduction of a ranking cycle. So watch out for an actual ranking cycle. Actual cycle is the one that you are given efficiency of the compressor, efficiency of the turbine. Then you're definitely going to have reheat. You're definitely going to have either cogen or open feed water. There will be no question on a combined cycle right behind. Because if I give you that, then it's going to take the entire time you have to solve just one problem. And I don't think it would be fair to you guys to have only one question. And if you make a mistake, you end up with a 0. So you don't want that. So, and I'm not going to do that to you. So it's becomes fairly simple. all you need to study the main concept of a simple ranking cycle and watch out for, the efficiency. Make sure, don't make the same mistake on the first exam. Show the efficiency on the TS diagram. Without TS diagram, you cannot solve a problem. Don't forget that. And then, that's it, solve a problem. Reheat. Remember, when we have a reheat cycle, we have two Q that we have to add them together in order to find the total Q in. One is the Q of the boiler, one is the Q of the reheat. Don't forget those. In open feed water heater, don't forget to find the value of Y, the extraction that we take from the turbine. Don't forget that. And if it's a cogen, don't forget that 0.4, we solved a problem last week, is between 0.2 and 3. And 0.4 is the base of the pump, not 0.3. That's what everybody made that mistake. So don't do that to yourself. By the way, there is a possibility on a reheat cycle, instead of 2 turbines, you end up with 3 of them. So that means twice you go back to the boiler and reheat, come out, and go back again, reheat, and come out. So watch out for that also. When we're talking about reheat, it's the whole thing. There will be no combination of a reheat and open feed water heater. There won't be any question about 2 feed water heater in one, cycle, so you don't have to worry about that. Possibility of those going to be on your final exam. Is there any questions? Now I have a question. Last week, I set up a problem for a combination of a reheat and open feed water heater. Gave you all the information, I'll set it up, and I ask you to, on your own, do it and see what you get out of it. Did anyone in the 36 people in the class make an attempt to do that? Any one of them? Now, you took this class, you are trying to become a mechanical engineer, and you know the importance of this course. And this is the second time that I did this. And I asked you to just, on your own, solve it. No big deal, just to help yourself. Last time, nobody did it. This time, same result. That's fine with me. Trust me. Everything I do here, try to help you guys. If you don't want to help yourself, there is not much I can do. Really, there is nothing I can do about it. So, that's where we are. Anyway, this is chapter 10. And now we're going to start on chapter 11. Now, did everybody make a note that the test is going to be on November 17th? Okay, there are 7 people missing, haven't showed up. Please tell your buddies in your project group when the test is going to be. So if you're done with this, I can erase it and start chapter 11. let me know when you finish. I can erase that.
I think we're good.
Beg your pardon?
I think we're okay with it.
Oh, okay,
Okay,
thank
Rich.
you. Chapter 11, we're gonna get into refrigeration cycle. Refrigeration cycle is basically opposite of the power cycle. Our power cycle, in power cycle, we input the heat in order to try to get the work out of the cycle. This refrigeration cycle is going to be totally different. We're going to remove the heat to get the cooling or refrigeration from that cycle. It's going to be a little different. So if you look at it, at this top part, we have high temperature, and that's called high temperature reservoir, or what we call it this time, sink reservoir. Now, if you remember, this temperature or this QH, this was the heat that we were putting into the cycle. This time, what we're trying to remove this heat from our cycle. Then here, we can have a compressor that putting the work into the cycle. Out here, we have T low or a low temperature source. In a power cycle, this was our source. This was where when we were getting rid of the heat. This time, we are looking for QL. So this is our high Q that we're removing. This is our desired output. This is what we're looking for. Before, we were looking what the power comes out there. As you can see, in a power business, we were going clockwise. Now we are going counterclockwise. We're going the opposite way. Now, if you take Brayton cycle, gas turbine power plant, and if you reverse the process, going in reverse, you have a refrigeration cycle. So There is an old saying, which is not accurate. If you take a power cycle and go reverse, you will have refrigeration cycle. That's not true, but that's how they want everyone to understand what was going on. Now, let's see how the equipment gonna look like. This is our compressor. This is work of a compressor we put into the system. Here we have a device, it's called condenser. You remember this. We use condenser to remove heat from our power cycle. We're doing the same thing. Our condenser does the QH for us. Remove the heat from the refrigerant. Now here when we come out, we don't have any equipment that we can expand because we know if we have a compression on the opposite side, we should have an expansion. We cannot, because we cannot take a cycle and keep compressing it. You pressurize something for a while, and after a while, it won't take it and it will blow up. It's like a soccer ball or a basketball. If you put air into it, it's fine, and you keep putting air as you pressurize it. At one point, that soccer ball, even balloon or whatever you have that you're pressurizing it, it will just explode. It will blow up. So we have to have something to expand. This time, we call this expansion valve. This is also called throttling valve. But we know that as expansion, it's much easier. Now, one thing about the expansion valve that you learn in your thermodynamic 1, delta H the expansion valve job is the opposite of the heat exchanger. Heat exchanger does not change the pressure. However, it will exchange the heat. Expansion valve will reduce the pressure drastically, but does not exchange the heat. So there is no heat exchange across expansion valve or through expansion. So if I call this point 1, point 2, and this is point 3, obviously this is point 4. So from there, that means H3 is approximately equal to H4. There is no delta H is 0 between the expansion valve. Remember that. Now, finally, here, in order to get the cooling that we desire, this time we have evaporator. Evaporator is another heat exchanger device that give us our desired output, which is QL. And this becomes our refrigeration cycle. We have workable compressor we put in. We remove the heat from the refrigerant through the condenser, reduce the pressure. This refrigerant becomes liquid. We take QL or cooling out of it, and then we start the cycle again. Now, QL is been called cooling load or cooling capacity. So that's what it's called. You will hear cooling load or cooling capacity of a cycle or equipment. That means QL. Now, how are we going to find the energy values across these equipment? Again, let me do the TS diagram first. The TS diagram, again, we're going to have a dome. The reason we're going to have a dome, because our working fluid here exchange, change the phases. So our working fluid is refrigerant. So in chapter 9, we had air as a working fluid. In chapter 10, we had water. In this one, our working fluid is refrigerant. And refrigerant goes through phase change. That's why we need to have a dome. Again, like before, anything under the dome considered to be a mixture. This side is a saturated liquid, that side is saturated vapor. Everything's all remain the same. Now, since we started going the opposite way, our point 1 would be located at a saturated vapor line. That's our point 1. Going to point 2 isentropically for workable compressor. Point 3 will be located at saturated liquid line. Since I don't have any equipment to go isentropically down, I'm going to curve this and come down to point 4. Point 4 is in a mixture. However, we made an assumption that H3 is equal to H4, so we don't have to worry about it. So this becomes our ideal refrigeration cycle. Now we need to define the processes of refrigeration cycle. Let me put this lower. Now, processes. Process 1 to 2 obvious isentropic compression. That means S1 is equal to S2. Process 2 to 3, it's isobaric heat removal. Process 3 to 4 is expansion valve. Which is delta H is equal to 0. Process 4 to 1, again, isobaric cooling at P4 is equal to P1, and this is P2 equal to P3. These are the 4 processes. So we have one isentropic process and 2 isobaric processes. This would be our QL, and this one is our QH. That is the work of the compressor. Since this changes the phase, so we have phases. Phase 1, saturated vapor. That's where the point is on a saturated vapor. Phase 2, superheated. Phase 3, saturated liquid. And phase 4 is a mixture of liquid and vapor. These are the 4 processes. These are the 4 phases of the refrigerant going on through that cycle. Again, keep in mind we go in the opposite direction. We have only work done on one side. Then we have QL and QH. Nothing's happening here. Find energy values. Again, there's a delta H cost equipment. So work of the compressor would be H2 minus H1, or just a small work. The QH would be H2 minus H3, and QL would be H1 minus H4. We always deduct the smaller value from the larger value. smaller value from the larger value. Smaller value from the larger value. We don't go by the subscript. H2 minus H1 at the top for the work of the compressor, QH, QL. If I want to find this big Q and big W, multiply this side, both sides by mass flow. So this becomes W compressor would be mass of refrigerant times H2 minus H1. This becomes QH, which is mass of refrigerant times H2 minus H3. And finally, QL is the mass of refrigerant times H1 minus H4. Now, our desired output is defined as the QL, the cooling load, cooling capacity. This is our desired output. Finally, the way we measure the performance of our cycle is not thermal efficiency. It's called coefficient of performance. We show that as COP. In your textbook, they also use data. The coefficient of the performance of the cycle is equal to desired output divided by the work that we put into a system. So our COP would be equal to QL divided by work of the compressor. We want this number as large as possible. The larger the number, the better performance we get from our cycle. Seldom you find the COP to be less than 1. The old days, the old refrigerant system, we would get that. But in today, we get all the COP more than 1. That COP of 5 or 6, 8, and 11. So that's what we're shooting, to get the highest possible coefficient of performance from our cycle. So this is the beginning of our refrigeration cycle. We talk about ideal, then we're going to go one step up to refrigeration cycle, and finally we get to actual refrigeration cycle. And we do a couple of more things with it, like we did in power cycle. So you'll see all of those as we go through. Any questions? All right. I will see you guys on Wednesday. I'm going to continue chapter 11. Don't forget your homework number 2 already be sent to you. So submit it on time. And I will solve the homework again on the board before the test. Have a good one.
Thank you, Professor.
Professor, have a good weekend.
Thank you.
Have a nice day.
Yes, do you have a question? Did somebody have any question?
I had a question. Just to, as a proper, like, so I can wrap my head around like what I guess my air conditioner at home does, and this cycle here. So I guess like the condenser and the evaporator and an AC, like let's say a window AC unit, there's that like a fan blowing in, and that's the evaporate blowing over the evaporator, and the fan blowing out, that's blowing over the condenser. Is that correct?
Yeah,
Oh, okay,
yeah.
got it.
Usually in a house, if you have a, what we call a split unit, you have your heat pump or air conditioning system in your garage, provide heating and cooling. And then you have condenser outside that has fan at the top of it. Every time you turn the air conditioning, the fan starts blowing and remove the heat from
Oh, okay,
it.
got it. Okay. What does, I guess I see what theoretically the expansion valve is, but I've never like seen it in person. Like what, is it just like a, I guess something that, is it like the input, I guess the pipe is small and then it gets big and expands into the evaporator? Or how does that expansion valve work?
The expansion valve just reduce the pressure because you don't want to take the high pressure to go in your evaporator.
Mhm.
So evaporator is just a heat exchanger, doesn't change the pressure.
Mhm.
Pressure 1 and 4 are the same, pressure 2 and 3 are the same, because you have two heat exchangers, they're not changing the pressure, they're just changing heat. One is removing the heat, one is provide cooling.
So it's like a throat that opens up and
This,
it just expands.
yeah, this is what just opens up, all of a sudden the pressure drops. Once the pressure drops, this becomes liquid. And once we take the QL out of it, becomes saturated vapor.
Got it.
Back up it and keep on, cycle.
Okay. I really want to take apart my air conditioner now just to see.
Yeah, well, we can do that.
Yeah. Okay. Well, thank you very much.
I'm afraid when we talk about your refrigerator, you're going to take your refrigerator apart too.
I just want to see how things work.
Okay.
Great. Thank you.
No problem. Did you guys have any questions?